Hello, my name is Kristen Hartsfield, and we are the Automated Solubility Measurements Project. We designed an experimental setup that will calculate or at least get a good range of what the solubility of untabulated solutes and solvents are. An important part of this is automating this entire process. So this involved automating the performance of titration tests, so the combination and mixing of the two different components of a solution, and also a data acquisition system. One component of our data acquisition system depends on an LED light shining through our solution, which is in a beaker. Two RGB sensors will pick up how this light scatters throughout the solution, and this also depends on its concentration. Due to this, we want to enclose our entire experimental setup inside of a dark environment, hence the black box. This will keep out any ambient light from affecting the readings for the RGB sensors and also helps to house our entire experimental setup. The IKA magnetic stir is one of the many components that we automated using Python code for our project. When the box is enclosed, you can't use the knobs and screen on the stir itself, so then it was really important to be able to start and stop and change the speed of the stir while it was enclosed inside of the box, so you wouldn't disturb the RGB sensors or anything else in the experiment. And so in this video, you can see an example using the ramping up file. And this code, this body of code, starts the magnetic stir at a specified speed and increases it by, say, for this example, it was an increment of 10 RPM through every code loop. And then you can also set a final stirring speed if you wish. There are also a couple other files and functions that could be of use developed in Python. The IKA magnetic stir has a very simple and easy user interface. So if you wanted to use this on your own, outside the black box, or in a different experiment, it would be really easy to change the speeds with just the knobs and the screen on the stir itself. There are directions in the IKA user manual that is uploaded on the supplementary instructional packet. Magnetic stir.py is a very large Python file that was developed by Dr. Jason Hines' lab. And essentially, this file allows your laptop to communicate with the IK stir and allows certain functions to operate. Stirring rate ramp test.py was the example file that I ran in the video in person in the lab. And so I'll walk you through it if you wish to use it. And so RPM initial is the first speed, the initial speed that you want your magnetic stir to start stirring at. RPM interval is the amount that you want your stir to increase through every time period. And RPM end is the final speed that you eventually want your stir to increase to. Time mix is the amount of time in seconds that you want your stir to mix. And then time wait is the amount of time that the stir will stop stirring and wait until the next stirring period begins. You also need to identify the COM port for which your magnetic stir is plugged into. Since it is through a USB connection with your computer, there are various COM ports that your laptop may identify, and you can do this through searching. It depends on your Windows or Mac laptop how you can identify a COM port, but a quick Google search on how to do that will help you out. And so here are various functions that will control the stir behavior. Start just starts magnetic stir at the specified speed for that period. Wait will tell the stir to continue to stir at how long you want it to stir for, and that would be your time mix. Stop and wait will stop the stir and wait the amount of time that you want it to not stir. And then your sequence will just loop through all of these functions, which will start at whatever speed you desired. It will continue to stir, which is wait, and then it will stop and wait and then begin again. And then here is the while loop in this Python file that will keep that running until you're at your end desired speed. If you wish to just periodically stir it without increasing the speed, you can just change your RPM interval to 0 and make sure your RPM end is not the same as your RPM initial. And then it will eventually keep running at the same RPM periodically. And this will help control your magnetic stir so it stays at the same speed, and you can also change how periodically it will mix for. Stir control was made to separate out a couple functions that were really important to our main file. It's also simplified the functions that were made in the magnetic stir file, and so those would be just starting the stir at whatever speed we chose, making sure we can keep the stir going for a specified amount of time, and then just stopping the stir. So stirring start just starts the magnetic stir at whatever RPM we would choose. Stirring wait would ideally be placed and called right after stirring start in another body of code. And this just tells magnetic stir to keep stirring for how long we want. So if we want it to run for 30 seconds, then we would just type in 30 for beat. And then stirring stop just simply stops the code. So if you were to put this in another body of code and wanted to call this in a sequence, you could easily just call these and use these and replacing A and B with whatever values you would choose. Stir test is an example of the functions developed in stir control just to show how it would be used. So we want to start the stir at 100 RPM, and so we would simply just call this in a separate file. Initially, too, we would have to import our functions into whatever code we are calling them in, and this is how you would type that in. So stir control would need to be in the file, the same file that we are having stir test run in, and then you can easily just import the functions that were created, which are the same names as in stir control. So you could easily check those back and forth. And so after everything is imported, we can just call our functions. So stir start would run our magnetic stir at 100 RPM. Stirring wait would tell the magnetic stir that we want to wait 10 seconds and continue to stir at the specified RPM. And then stirring stop would just stop the stir. So after this file has ran, it would just simply run the magnetic stir at 100 RPM for 10 seconds.
This is the pump that we used. The particular model is a Masterflex LS07551-20 peristaltic pump, which has a good amount of functionality that we'll talk about here. Fair word of warning, the pump's maximum resolution you're going to get out of it is about 1/10 of a milliliter when controlling through the pump itself, and about a milliliter using the code. So if you need more, go ahead and stop here. Here's the back of the pump. You only need the ports if you plan to hook the pump up to a computer and control it through code, so you can probably skip this part if you're going to do inputs manually. The power switch and the power cord are located at the bottom here. As for the ports for the computer to control, you'll have the USB-B, RS-232 in and out, and a DB25 port. Obviously, you can use whatever you want or have on hand, but our team found using the DB25 or USB-B was favorable just for the sake of having fewer cords. So now you'll see that I have the pump hooked up to power and switched on. From here, we're going to want to hook up tubing to the pump. Notice that this attachment only takes 15, 24, 35, and 36 tubing, which is technically less types of tubing the pump actually allows. We're going to be fine though because we're going to be using Masterflex 24 tubing, which will typically be written on the side, but since this one's old, it wore off. If you want any degree of accuracy, be sure to use Masterflex branded tubing and whatever they have listed. But if you don't care about accuracy and you're just trying to move some volume of liquid at some random rate, I mean, well, if it fits, it ships, I guess. Insert the tubing in here like this and attach whatever connectors you need so long as they're airtight. Now on to the fun part, controlling the pump. Everything here is pretty intuitive. D-pad, enter, play, pause, and this little number which just essentially turns the RPM all the way up while you have it pressed down, so as a way to fill up the tubing with liquid. As for calibration, you're going to want to head into settings, choose tubing size, and select your tubing. Now I have no earthly idea what the hell HPF stands for, but if your tubing says it, then choose that, I guess. For the calibration itself, go into tubing cal and then hit start. This is going to try to dispense 200 milliliters of liquid based on whatever tubing size you put in before. One end of your tubing should have that 200 milliliters of liquid and the other should be able to contain that 200 milliliters of liquid. Also, be sure to hit this button to fill your tubing before you start. Once it's dispensed what it thinks is 200 milliliters, input the amount of liquid it actually dispensed and voila, calibration. Now let's talk about the dispensing modes. This pump has 3 types of dispensing modes: time, volume, and continuous. To switch between them, just press enter on the current display mode. Time mode will dispense whatever you have your flow rate set to as for whatever time you see here. And it'll do that for me on the amount of batches you see down here. The batches will have about a 5-second delay between each batch just to give you a rough idea of what it's going to look like. And when you have everything set up, just press play. Volume display mode is pretty self-explanatory. Select the volume that you want to have dispensed, and again, down here's the number of batches. Continuous mode is more of the same. It'll run a specific RPM or flow rate, but obviously doesn't have the batch feature. For every mode, just use the play pause button as a start-stop. Now I'm going to talk about the pump code with you. So the Masterflex class is just a file that we pulled off of GitHub. If you, for some reason, find yourself in need of this file and don't have access to our project, just look up Masterflex peristaltic pump Python on Google, and this should be the first result. The particular file only works with specific Masterflex pump models, so be sure your pump model is a Masterflex LS pump models 07523-80, 07523 90, 07551 00, 07551 10, 07575 10, or a later version of any of those pump models works as ours is a 20. Now, this piece of code does a lot of things, and I, as a mechanical engineer, can't possibly begin to comprehend those things. So for now, let's just talk about what we need to use, at least for our scope of the project. At the bottom, you're going to see a list of all of these different functions that we can use, these different commands. And we're only actually going to use 3 of them. There is set motor speed, if I can find it. Set motor speed right here. There's also set revolutions. And finally, there's halt right here. Now, there's actually a lot of other functions that are pretty useful for getting data, like request motor speed, for example, somewhere down here. But like I said, the 3 that I mentioned before are the only ones that our code uses. So set motor speed does exactly what you think it's going to do. You just need to pass it the pump object that you're using as well as the RPM that you're requesting. Set revolution is the same, but with revolutions, and halt just stops the pump. So it's really useful in logic statements and the like. I spoke kind of briefly earlier about this, but it's important to establish a relationship between RPM and flow rate, as well as revolutions and flow volume. This can be pretty easily done by running the pump at some RPM for like a minute, then recording that volume that was outputted and plotting the results. If your results aren't linear or extremely close to linear, I would suggest calibrating the pump, because by and large, these pumps are expensive, and they're going to give you really consistent results. As for the code our team wrote, you'll see here in the pump stuff file at the top, you can see there's a global variable, total volume, which tracks the total volume of the fluid dispensed during the experiment. Working our way down, you'll see initialized port here, which just opens a channel to the Raspberry Pi. If you want to, for example, choose a different type of port like Linux or PC, you're gonna need to change this little statement right here, this port variable. Stop flow calls a halt function for a past pump object. Set flow vol is a function that converts the requested volume to a number of revolutions and then dispenses that provided the beaker overflow condition has been triggered. Set flow rate pretty much does the same, except it does it for a continuous flow rate rather than a set flow volume. You'll notice that both of these functions, there's a catch condition, so that you'll be able to request, so you have to request a positive flow rate or volume. You can't ask for too high of a volume or flow rate. There's also conversion functions, which are at the bottom of our code here. Now, these are dependent on what you guys are testing for. Obviously, these conversion functions are specific to our pump, the way we had it set up. So you're gonna pretty much have to adjust. This is one of the parts you're probably gonna have to edit, just based on what your RPM to flow rate and revolutions to flow volume conversions you get are. Now the set functions also share this big red button function here. All this is going to do for us is check if the total volume dispensed has eclipsed 80% of the beaker volume, and if it is going to stop, it'll return false as well. Otherwise, it's just going to return true. So that's kind of very useful in logic statements. The function was actually originally set up to throw an exception when the capacity was hit. So that's just an idea if you feel comfortable or want to pursue that in lieu of, having a logic statement here instead. Other than that, these are just return functions that are going to give you values that might be relevant to the experiment. For example, if you need the total volume somewhere else, get total will give that to you, and get percent will give you the percentage of the capacity of the beaker that's been filled so far.
So here I'm going to talk a little bit about the LEDs that are used in order to judge the turbidity of the solutions. You can see the red, green, and blue LEDs right here. They shine into the beaker, which is placed atop the magnetic stirrer. Each of the LEDs is individually switched, which I'll cover in just a moment. There are red, green, and blue LEDs, and the light scattering of these is measured by the RGB sensors. As you can see there, that I'm doing in the video, there are individual switches for the red, green, and blue LEDs for the beaker that sits on top of the magnetic stirrer. You can turn on or off the red, green, and blue LEDs at your choosing. And because this is a black box environment, those lights should be the only source of light within an experiment that's run in the box. In just a moment, I'm going to show that the lid is going to flip over and go over the top. So that's kind of how that's done. You flip the lid over, you place the beaker on top, and you have those switches which are accessible even when the box is closed. So here is a little bit of a close-up detail of the three switches, red, green, and blue. You can see they're labeled there. These are nice switches. They're a nice tactile, clicky feeling, and they also light up when they're turned on, so that's a nice benefit as well. Here's a closer look at the way that the circuit is powered. You've got the battery pack here in my hand connected with Anderson power pole connectors to a power distribution panel, which ultimately provides power to the switches here, and the switches are single pole, single throw. Hey everyone, next up I'm going to talk a little bit about getting the Arduino working. That's the Arduino right over there. You can see that it has the red shield on top. That shield contains these 4 ports which are used for interfacing the conductivity sensor. Make sure you plug the conductivity sensor into one that's marked analog. If you look over here, you can see analog, analog, digital, digital. Make sure it's plugged into one of the analog ones as it is an analog sensor. This is the actual conductivity sensor right here, and this little box just kind of facilitates the connection of that. The Arduino, like a typical Arduino, plugs in with a standard USB cable, USB type B, the full size like you might see on a printer on this end, and USB-A on this end. This is just a USB-C adapter for my computer in order to have access to a USB type A port, which is right here. You can see that on screen I have the file cond_sensor1. It's in Arduino's IDE, Integrated Development Environment, which is available for free download. If you Google Arduino IDE, it's a quick download available for Mac, Windows, and Linux. Do note that you need to configure the board and the port. This is an Arduino Uno, so as you can see here, I'm going to Tools, Board, and Arduino Uno is selected. And under port, you can see under serial ports, it's not the Bluetooth one, but it's this one, USB modem 143401. This will look a little bit different on Windows, but it should be pretty similar. And also note that we are using a baud rate of 9600, 9600. So you can verify the sketch, compiling it. You can see that it says done compiling right here. Once you've selected the board and the port, then you go ahead and click on upload, or you could do Command U. And once it finishes uploading, you can see it says done uploading now. Now you can open up the serial monitor, where you can hit Shift Command M. And as long as the baud rate is set to 9600 right here at the bottom, 9600, you can see that it's reporting data. So each one of those is a measurement. Right now it's showing 0.00 because ideally air should not be conductive, or very, very not conductive. And there you go. That's how you do it. You can show a timestamp if you'd like, or not. And that's how it's done. Welcome back. And here is part 2 of the Arduino tutorial. Because in part 1 we had the Arduino, that's this piece here, connected directly to the computer, but in our project hardware the Arduino is actually connected to the Pi. It's just useful sometimes to connect the Arduino directly to the computer when you start debugging, just to make sure that's working before connecting it to the Pi. But this piece right over here that I'm pointing to is the Raspberry Pi. That's a Model 3B that we're using. This setup is unchanged. You can see that the conductivity sensor is plugged into one of the analog ports on the red shield on the Arduino. That is completely the same as in part 1, but this time you'll notice that this blue USB cord that starts with USB type B and ends in USB type A, that is no longer plugged into my computer. Instead, it's plugged into the Raspberry Pi, because that's how the Pi grabs the data stream from the Arduino. The Raspberry Pi in turn is connected to my computer with an Ethernet cable. That's this jack right here, plugged into the same USB-C multi-port adapter. And you can see on the computer screen now, instead of the Arduino IDE, I have Microsoft Visual Studio Code. Like the Arduino IDE, Visual Studio Code is available on Windows, Mac, and Linux for a free download directly from Microsoft. It is a pretty large download, so it's not going to be a quick one. But once you get that going, then it should be just fine. You can see on screen I have the file serial conductivity rev1.py, serial underscore conductivity underscore rev1.py. We took care of assigning the USB port name because, similar to a COM port on a Windows machine, the Pi is going to assign a name to the Arduino once it's plugged into that USB port on the Pi. So we took care of that. And running this, you have two options. You can either hit the little play button in the top right hand corner here, it's kind of this little green button, or you can hit run from the run menu at the top. So what this will do is, and I don't have the power supply for the Pi, but it would be plugged into the micro USB port on the Pi. And if I had that with you, I would show you plugging the Pi into power, turning it on, having an SSH connection into the Pi from the terminal, running this file, and then you would see the same data stream you saw in part 1. Hope that's helpful.
Landing page of our GitHub repository. This website gives you the necessary link to download all the files to your host machine using the git clone command from terminal. Here we have listed all the Python files necessary to operate our automated solubility system, which you can see here in the first figure of our README. Just below that are the links necessary to install the dependencies for this project. Each link should take you to a page that will give you a command that you would run in command prompt, as you can see here. The format of this command is pip install and then your package name. So now I want to direct your attention to main RGB2. This file carries all of our imports and calls functions from all other Python files that you see listed here. I'll go ahead and click on it to show you what's inside. Here on the first line we have a bash command telling the Raspberry Pi or whatever computer you're running this on to only run this Python file in 3.7. Our team found issues with later Python versions as there was a dependency issues. Please remember to install Python 3.7 before running this file, or change the version at the end of this command to your current compatible version of Python. Lines 3 through 40 are all imports for various sensors, equipment, and functions we'd like to call. The comments in this code indicate which is which, for example, import for pump, import libraries and modules for magnetic stir. Lines 46 through 53 deal with asking the user to input information about the experiment and their email. Right after that, we have an initialization of the RGB sensors, which use the Adafruit Blinka library, which should have been installed earlier when you were installing dependencies. We then initialize our arrays and ask the user if they want to calibrate the sensors. It's suggested that you calibrate the sensor each time before use. Line 102 performs a signal-to-noise ratio test, prompting the user to switch colors. We then turn off the incident light measurement on the LEDs and reinitialize some things. We then take an average of the RGB index of the liquid inside the beaker using this for loop. This value is stored and used to compare against current RGB values. This while loop at line 155 and ends on 166 is meant to continuously dispense salt, stir, and measure RGB indexes until we are sure that there are undissolved salts in the solution. As you can see here on line 170, we are now using sensor 2 to get the grayscale value and setting it as a goal. In our solution, Sensor 2 will be the top sensor in the experiment since it has the best estimate as to what the solution looked like at its solubility point. On line 172, we initialize a difference variable that will constantly update in this while loop that you see below it. This while loop also has a big red button function attached to it, which will stop this whole while loop if a beaker gets too much liquid and starts to overflow. Inside the while loop, you can see that we have an if-else statement that dispenses varying amounts of liquid depending on how big the difference is in our solution. We then tell the magnetic stir to turn on and stop. That way we can be sure that all the salts have been dissolved into the solution. At the end of this else statement, we have an alert that will send an email to the email address that the user had inputted earlier, notifying the user that the experiment had failed or that the beaker was getting too close to its overflow parameters. Below that, you can see the code grabbing data from the information that the user had inputted earlier, such as the mass of the solvent and the volume of the solvent. These while loops ensure that the data inputted into the questions at the beginning of this experiment are only numbers. And here at the bottom you can see the parameters that the user inputted at the beginning experiment and the total volume of liquid dispensed in this experiment used to be calculated the concentration. And here at the very end we add all of this data to our XLS files. Python file responsible for dispensing solids in our automated solubility experiment. The first two lines are responsible for our imports. We import time and sleep, and the second one we import RPI, GPIO as GPIO. You'll have to install this dependency to get this file working. Lines 4 through 8 are some global variables that we use throughout this code. The first two are declarations for the pins, which can be found on your Raspberry Pi. Line 6 and 7 are declarations for our directions. Counterclockwise will be set as 0, clockwise will be set as 1. And steps per revolution are set at 200, but that can be changed depending on your motor. The NEMA 17, which we use in our experimental setup, can go up to 1600 steps per revolution. Lines 10 through 13 set up the pins that you have connected to your stepper motor as outputs, and then it declares the direction to be clockwise. Lines 16 and 17, we initialize some variables, so step count will be equal to steps per revolution, and the delay will be 5 milliseconds. Since we've already set the direction on line 13, we run the for loop on line 20, which turns on our pin and then turns off our pin, sending a data pulse. This moves our motor forward. Line 26, we make the stepper motor sleep, and on line 27, we switch the direction of our stepper motor and repeat the same code that you see on line 20 on line 30. This makes up the entire file for dispensing our solids, and you can change any of these parameters to your liking.
Hi, this is Yasin from Team 25, and here I will instruct the Python code file for serial communication of the conductivity sensor. Since the vernier conductivity sensor is connected to the Arduino Uno with the interface shield, and the Arduino Uno is connected to the Raspberry Pi with USB port, we need a serial communication Python code file for the Raspberry Pi to get data from the Arduino Uno. Right here, we import all the necessary module, and its number function here is just to check if the input is number or not. Since we in up did not use this function in the in, I'm not going to explain too much about this here. So the initialize conductivity function is for the serial communication between the Arduino Unos and the Raspberry Pi. In line 30 and 31 here, it do the serial communications, find the path name of the Raspberry Pi, and the connection, the burn rate, and timeout. And in this line, it wait until all the data are read out, return the result, the serial communication result. In the conductivity function, it has the serial communication result from last function and the empty list time for list as the input. Read the lines, and the result is in string type. The result file is the digital number of the result. So add the current time and day into the time list. If the length of the result flow larger than 0, which is always true when using this sensor, the result flow will equal the first item in the result flow list. Add the time, current time, and day into the list again, pen the result flow, and have the result flow as the output of this function. This function is also the function we're going to import in our MAE file. And this serial communication Python code does not only allow the serial communication between the Arduino Uno and the Raspberry Pi, it also allows serial communication between other Arduino product and the Raspberry Pi. This Python code file is for the DS18B20 temperature sensor used in our system. We obtained the code from Circuit-based website and twist it a little bit so we could use it in our system with other device and sensor, and also use it individually. We add the code block to allow temperature data and the time data to export into Excel file. So right here, we import all the necessary module. In line 11 and line 12, we set up the connection with one wire. Since in one wire interface, GPIO4 pin is the default pin, we have to connect the data wire from the temperature sensor to the GPIO4 pin when we're using this sensor. So right here, we find the path name of the file for one wire device in Raspberry Pi. Obtain the path name and use it in the red temper route function here. So we open the device file, read the data, and save it in lines. Save the data string or the data list in lines, and close the file and has the line as the output of the function. So in red temper function, we use the result from last function and use while loop and check if the data come from the sensor. And subspan execution of the calling thread for 5 seconds here. We get the result from the last function again and check the data position in the data string here. So if the position of the data isn't the position of the old data right here, we will get the temperature data from the temperature string. And this two line is to find the current date and time and limit it to only the current time, which is shown in hour, minute, and second. We get the temperature in Celsius, and then use a sample conversion equation to get the temperature in Fahrenheit. And we have the current time, temperature in Celsius, and temperature in Fahrenheit as the output of the red temper function. So if we want to use this individually, we need to uncomment this to code block. We uncomment it by just the highlight of the code block and plus control plus slash. So this Excel create function will grab the activate workbook and assign the data or the information into the cell directly using the for loop to assign the temperature data and also the time data and the temperature data into the Excel file. And if we want to use it in the MAE file, we just have to keep this to code block comment out and import the red temper function in the make file. The temperature sensor has 3 wires as shown here. So in order to use the temperature sensor with the Raspberry Pi, we need to connect the 3 wire to the Raspberry Pi. So 1 wire is for the power. We could either connect it to pin 1 or pin 2 here, which is the 3.3 volt or the 5 volt power. And one is for the data wire. And for the data wire, we need to connect it to pin 7, which is the GPIO4 pin here, because in our code we have set the GPIO4 pin as our data output pin. And the last wire need to be connected to pin 6, which is the ground pin here. The temperature sensor requires 4.7K ohms resistor to operate this system. In our system, we have the resistor and the PCB, the wires soldered to the PCB, and everything is set up for you, so you could just run the MAE file. But if you want to use the temperature sensor individually, you could either use a resistor device like me, or you could use a 4.7K ohms resistor with the breadboard. So in order to use the DS18B20 temperature sensor with the Raspberry Pi, we need to enable 1 wire in Raspberry Pi first. So we enable it by enter the following command to open the utility, select interface option, select 1 wire, select yes, okay, and finish. And now we could test the code. And here we'll show the time and the temperature in Fahrenheit.